Lesson 6 is key features from tables of quadratics, and in 6.1, we're just going to analyze a couple tables and pull out as much important information from those tables as we can. So in example 1, we have an input-output table, x values on the left, f of x is on the right, and remember that f of x is interchangeable with y. It's basically, I would like you to consider it like the x values or the left side of the table as all of our input values, and then the right side of the table where it's f of x or sometimes y is written is all of our output values. So most of the time, your table is going to be set up on the left side, like with your x values, where the x values are increasing as the table goes down. So we go from -2, -1, 0, 1, 2, 3, 4. So all the x values are increasing. And then with the y values or f of x side of the table, it just kind of depends on what type of function that you're dealing with. So if we see what kind of movement our f of x values have, we're going from 0 down to -5, down to -8, down to -9. And then after that, it goes back up to -8, up to -5, up to 0. So it goes down and then it comes back up. And we already know that like these are tables for quadratics. That wouldn't be necessarily something that like you would have to just look at a table and figure out, but that information is given to us. So for a quadratic, it's called a parabola, like the shape of the graph. So it looks like either like this or like this. Either opens up or opens down. So since our graph is like kind of trending towards this, we'll say this middle point, like -9 was that point where it changed directions and it turned back around because it went from like 0 down to -5, down to -8, down to -9, and then it turned back around after that. So since that's the case, that -9, that's the lowest value. So whenever you have like a lowest value on our table, that's considered a minimum, like a low point. So our parabola would be the one that opens up because that's the one that has the low point. Because like over here, like these would go down forever. There's no actual like low point because it's infinite. So there's not an actual value there as the lowest possible value. And it's definitely not something that we could put on a table. So we found that point that kind of helps us figure out what the shape of our graph looks like, or not shape, but orientation. That point where it's changing direction, and there is a name for that point. The point where it changes direction is the vertex. So that means that this point, I'm gonna erase some of these arrows. This point, 1, -9 in the middle of our table is the vertex. Okay, so that's one very key piece of information that we found from the table. Whenever there's a vertex, there's either a maximum or a minimum there. So since our vertex, we already kind of sketched a graph and like can see that our vertex is the lowest point of our graph. That means that the -9 of the vertex is the minimum. So -9 is our minimum. And every single every single quadratic graph has either a minimum or a maximum. It can't have both, it just has one or the other, but it for sure has one or the other. So we have our vertex, we have our minimum. I'm going to just kind of sketch a side picture. This has nothing to do with our graph necessarily, but it's just kind of more of a reminder. So like, let's say I have an x-intercept on the graph. That's going to be the point, like x, whatever the x coordinate is, and then the y value is going to be 0. Like that's what makes it land on the x-axis, is that it has a y coordinate of 0. So if we have any points on our table that have a y coordinate of 0, those would be x-intercepts. So we have 2 of those points. So right here, there's a y coordinate of 0, so that's an x-intercept. And then down here, there's also a y coordinate of 0, so that's also a x-intercept. So x-intercepts are anywhere where the y value is 0, because that's what makes it so that we don't go like up or down with our point. We just stop like exactly on the x-axis. And then for a y coordinate, it would be the point like 0, and then whatever the y value is, because we're not going left or right, so x value would have to be 0. So to find the y intercept on the table, you would have to look for wherever there is a x coordinate of 0. Just trying to make sure I didn't misspeak. So we have an x coordinate of 0 right here. So that's going to be a y-intercept. I know it's kind of like, feels kind of backwards because to get the y-intercept, you're looking for an x value, and to get the x-intercept, you're looking for the y value. But it's just because, like we said right here, what makes something an x-intercept is because we don't go up or down when we're graphing it, so the y-coordinate would have to be 0. And then what makes something a y-intercept is we don't go left or right when we're graphing it, so the x-coordinate would have to be 0. Okay, so we have all those. We have x-intercepts, we have a y-intercept, we have the vertex, we have the minimum. And then now we can also describe like the end behavior of the graph. So I always like to sketch like a little picture like this with end behavior, or when I'm describing like where things are increasing or decreasing. I think it really helps me. So I would recommend it as well. So remember that end behavior, it always is structured the same way. So end behavior is just how, it's the way that we describe how the graph ends. So it starts off with as x approaches negative infinity, and that just means the left side of the graph. So x is approaching negative infinity. That's saying like the x values are getting smaller, and x values get smaller on the left side. We say f of x approaches, and f of x is like the y value, so it's just asking like, is it going up or is it going down, because that's what the y value controls. So like if we look at even just this little sketch right here, the left side of my graph finishes upward, so that would mean that f of x approaches infinity. And I think in I just realized, I think in your workbooks and then also in the video, I like write out the whole word approaches, but that like little arrow to the right, I'm just gonna make a note up here. It means approaches, and it's just kind of shorthand for approaches. So you are more than welcome to use that instead of writing out approaches every single time. Okay, so this is just basically as the graph goes left, it finishes up, because left is like the negative for x, and then up is the positive for y, or f of x. And then we also have to graph, or we have to write what the graph is doing like on its right side. So we would describe that as x approaches infinity, so that means as the graph goes right, because as x approaches infinity, the like x values are just getting larger and larger. So as this graph or the little sketch goes right, what is it doing? Is it finishing going up or is it finishing going down? This side is finishing up and to the right also, so that would mean that f of x is approaching infinity as well. So if it approaches infinity, or sorry, if the graph is finishing upward, f of x approaches infinity. If the graph finishes downward, it would become a negative infinity. So end behavior as x approaches negative infinity, f of x approaches infinity, and as x approaches infinity, f of x approaches negative infinity. That's discussed, like end behavior is discussed in more detail in lesson 5. So if you happen to like miss that lesson and you're looking at this a little confused, I would definitely go back and watch it. And then the last one, or kind of last piece of information that we can pull out, is where the graph is increasing or decreasing, which I like to use this little sketch also here, which it's kind of cool because like you don't even have to graph the whole thing. You can just know essentially the shape or like the orientation and then the vertex, and it can tell you all this information. So I know that like the vertex from my table is the point 1, -9. So if I follow this graph from left to right, it starts off going down or decreasing, and then it hits the vertex, and after that it goes upward. So since I'm following it from left to right, my like boundary line is the x coordinate of the vertex is that 1. So it's like going down until it hits 1. Like picture the 1 as like, this is the line x equals 1. So it's decreasing until it hits that line, and then it's increasing after it. So we would describe that as decreasing, and then we could use interval notation just to kind of shorthand it. So since it's decreasing to the left side of that line, that would be from negative infinity to 1. And then remember with interval notation, use parentheses or brackets, and brackets would mean that it includes that number. You can never include infinity, so that would always have a parentheses around it. And then at the vertex exactly, it's not increasing or decreasing, it's like completely neutral. So that's why I would use a parentheses here. And then for increasing, it's increasing after that line. So like this section over here is where it starts increasing. So after that would be between 1 and infinity, because it's like where all the x values get bigger and bigger. So it'd be 1 to infinity. It's anywhere on the right side of that line. So it's decreasing between negative infinity and 1. So that just basically means the left side of the line x equals 1. And then it's increasing between 1 and infinity. And then this like interval notation, same thing as in lesson 5. So if you missed it, I would definitely go back and watch it. Okay, so I think that's a ton of information. I feel like that's a very good amount of information to pull from the table. So we're going to move forward to example 2. Okay, so example 2, we are not going to go through and find all that same information because it's a little bit tedious. It's basically the same process. But we are going to identify the vertex just because this is a little bit different with this one. Okay, so you can see from the left side of the table, like our x values are increasing again as we go down. So it goes from -4 to +3. And then our table is kind of trending the same way. This time it goes up as it goes to the middle of the table. So it goes from 0 up to 6, up to 10, up to 12, and then it's at 12 again. And then it's back down to 10, and then back down to 6, and then back down to 0. So it doesn't increase to like a single point like this table did up here. So like over here, the -9 was like a one-off. It was like in the middle of each one where like these two were the same, -8 and -8, -5 and -5, those were all the same. We don't have that with this table. We just have like these two -12, so it's almost like we're missing the vertex, and we are like that's kind of the point. The problem is that we're missing the vertex right here. That's where it would be. It would be perfectly in the middle of those 2 points. So if we need to find them, we're just gonna basically have to estimate it. We can't actually find the exact vertex unless we know the rule, which is like the how we would write the function, or how we would write the like kind of equation, for lack of better terms, for this table. So I'm just going to pay attention to like how much we're increasing or decreasing by each time. So we know that like our x coordinate of the vertex, like if it's right here, we could definitely find like what's in the middle of -1 and 0. So middle of -1 and 0 would be -0.5. So we got that. We can do that. The other side is where it gets a little bit funky and we just kind of have to estimate. So I'm just going to look at what we're increasing or decreasing by. So from here to here, I went up 6. From here to here, I went up 4. From here to here, up 2. And then I'm going to go like the reverse. So this is up 2, up 4, and then up 6. So I know like there is a trend there, like it's increasing by, or increasing or decreasing, depending on the way you look at it, by 2 each time. But if I were to like continue that pattern, it would be like +0, like 6, 4, 2, 0. And that doesn't make any sense because we know it's going to go up at some point, because we can't have like two vertices. We can't have 2 of them like in 2 different spots. There is that one central point. So that +0 part just doesn't really make sense. But we know that it's going to be something less than 2. Like just the way that it's trending, this increase has to be less than 2. I'm going to write less than. Must be less than 2. So that's really all we know. Like we cannot find the exact value. We can only estimate it. And we have to know like, okay, so it's increasing by less each time. It goes from 6 to 4 to 2. I can't keep going down by like 2 because that would bring me to 0, which wouldn't make sense for the problem, but I know that I can't increase by any more than 2. So if I'm starting at 12 and I'm increasing for something by something that is less than 2, there's a pretty finite like gap that my number can be. So it's perfectly fair for us to estimate that it's going to be between 12 and 14. So that value that's between these two 12s, like if they're each increasing by something that is less than 2 to get to that middle point on the table, it's perfectly fair to just say, okay, that number is going to be between 12 and 14. And I know it's not very like satisfying, but that's sometimes in math you just have to estimate. And based on the information that we have, like that is the best that we can estimate. So that's all it is, between 12 and 14. And then I'm just going to say, I'll write it as a point because it asks for our vertex. So we'll say the negative 0.5, that's not an estimate because it would have to be between like halfway between 0 and negative 1. So I'm going to say negative 0.05 and then between 12 and 14. Okay, so you should have something that pop up like that in your workbook. And then, like I said, you're just estimating to your best ability based on the little information that is given to you. Okay, moving down to 6.2. So the main goal of 6.2 is for us to recognize that quadratics have symmetry and they have important points. And so maybe if we're given a whole table, we don't have to graph every single point. So yes, like if we're using the points to graph, we can just take every single point and put them on there, but it's more about efficiency and knowing that we can sketch the graph without taking the time to plot every point. So let's identify the vertex and then maybe some other important points on the graph. So we know that, okay, the left side of the table is like going from 0 up to 6. And then if we watch the trend on the right side, so it goes from -7 up to -2, up to 1, up to 2, and then back down to 1, back down to -2, back down to -7. So this middle value must be my vertex. So that is absolutely important. That has to be on your graph for sure. So that's our vertex. And then depending on what the problem is asking, a lot of times it's pretty important to have the intercepts. So I would always just get in the practice of identifying those from your table. So remember for a y-intercept, it's a point on the y-axis. So in order for a point to be on the y-axis, you need an x-coordinate of 0. So this point is our y-intercept. And then just check to see if there's any x-intercepts. I would argue that x-intercepts, if you have them on your table, are probably more important than y-intercepts because x-intercepts show you what your like zeros and solutions are. But just looking at this table, the x-intercepts would have a y-coordinate of 0, and we don't have any that have a y-coordinate of 0. So we don't have to go and look for it. It's just you would have to, or you would want to identify it if it was there. So we have those 2 points. I'm going to go ahead and graph the vertex. So that's at 3, 2. And then my y-intercept is at 0, -7, so down here. And then technically, like, quadratics are symmetric. So if you were to just go like this, and then you know it's going to go the same side, like down on the opposite side, so like this, like that's a perfectly good sketch. I don't like, I'm not a huge fan doing that. I like having at least a third point, but the kind of workbook text emphasizes that you can do that. I would just make sure that you're trying to keep your like sides of the quadratic like reasonably symmetric. I know it's hard when you're drawing it by hand though. But if you don't want to do that, like I don't really like doing that, you could just kind of pull this other point down here that's opposite of the other point that you have on your graph. So these were like equidistant from the vertex. So it's just going to give you that other point over here, which is 6, -7. And then I think that makes it a little bit easier to make it fully symmetric. So we'll draw down through here. And then we have quadratic. But like I said, I mean, if you want to graph all the points, you can graph all the points. It just takes a little bit longer. So our goal is to be more efficient, but I mean, do what you need to do to get to the correct answer.